So I think next class we can spend time reviewing some old exam questions. That might be useful to you. Well, it's useful, I think, to see, especially if you missed some points, and then we can clarify that. By the way, if you have questions about some previous homework where you lost points and you aren't sure why, and you want me to explain in more detail or go over some old homework question, just email me by tomorrow. If you email me by tomorrow, that it's better for me to go through some from this homework, that problem, then I will be happy to review them next class. Well, it is hard for me to know where the doubts are if you don't let me know. Okay, so yeah, I think that will be a good exercise. I have posted one practice exam from last time, so you can surely review them. I would be happy to provide you another sample exam from 2016 as well, and I will try to find it, and certainly I can provide that as well. Okay, so with that, I just want to go through a few more ideas once again without really going into detail of these ideas, because we don't really need to solve homeworks. The goal is to just walk through a few ideas and just to give you an appreciation for things and not really talk about in greater depth. That said, you can always learn in greater depth if there is a need. Okay, so how do we go from pipelining the so-called constant coefficient recursive digital filters to the adaptive filters? So the first step, before we go to adaptive filters, the first step is to try to understand just a time varying filter. So still the next output yn plus 1 is no longer a constant coefficient a times yn, but in this case an, the time varying coefficient. So I'm not still talking about how that an is being adapted, so that's a separate part, but let's just take a look at this time varying recursion plus the input un. And so if we take that first order equation and apply look ahead in to that equation, then we can express yn plus m, that's the output m steps from now, as a function of yn, that's the current output. So and you will see that all of these terms are the pre-computation terms, so we can pre-compute these, and they are not going to be part of that feedback loop. And just like the FIR filter, in the look ahead decomposition, these will be outside the feedback loop. But what we see here is, instead of a term like a to power m or a to power m, now we have this product over 0 to m minus 1. So that's product of m quantities, and these m quantities are a of n plus m minus 1, n plus m minus 2, all the way up to a n. So when I equal to m minus 1, then that's just a n. And there are all these terms here. So if you look at what that equation looks like in terms of the structure or the block diagram, so the that coefficient that I talked about as part of the feedback loop, an plus 3 times an plus 2 times an plus 1 times an, so that product term of 4 quantities, in this case 4 things being multiplied together, and that's going to be input to that multiplier as part of the feedback loop. And if you look at this pre-computation part, outside the feedback loop here. This is the feed forward part, and that is so that expression is here. So un plus 2, so there is 3 delayed by 1, un plus 2 times an plus 3, and then un plus 1 times an plus 3 times an plus 2, and then un plus 1, un times, so 3 delays, un plus 3, 3 delays, so un times, this is an plus 3 times an plus 2 times an plus 1, and add them up, and that's going to be the pre-computation part. Okay, so there are a lot of simplifications that we can carry out to pipeline the least mean squared adaptive filter, and so the number of simplifications that we describe here. By the way, I should mention that this was all PhD thesis work of my third PhD student, Naresh Sandbag, who is a professor in University of Illinois Urbana. Okay, so the first so-called relaxation, product relaxation. So what the product relaxation says is that I can approximate that product. So the product here that is computing the product of m things. In this case, m is 4. We are computing the product of 4 things, and then we can just approximate that by a simple term like that. So if you look at how this approximation idea evolves, so think about, so we are starting with some product of an plus I equal to 0 to m minus 1, so that's like an times an plus 1 times an plus 2, etc. Okay. So if we assume that these a coefficients aren't changing a lot, and that's a big assumption, of course. All the relaxations are approximations, and these approximations are based on certain assumptions. And so if I assume that the coefficients, think about a lot of Whiteson stationary processes where the weights are varying slowly, and that means the weights that are being adapted aren't changing rapidly. Okay, so if the weights are changing very rapidly, that would be a non-stationary random process. So it wouldn't be Whiteson stationary. Okay. So then we can approximate this. Okay, so if it is changing slowly, I can say, okay, all the product of these m things is simply the most recent coefficient raised to the power m. Okay, so that's kind of the first approximation. And from that we go to the second approximation again. So if the quantity a, the weight parameter, is assumed to be close to 1, then I can write that as 1 minus some epsilon raised to the power m, and then 1 minus some epsilon raised to power m can be approximated as 1 minus m times epsilon. Okay, so these are approximations. And then substituting epsilon back in terms of a, so that would be 1 minus m times 1 minus the coefficient a. And if m is a power of 2, for example, there is no multiplication involved. So essentially we have gotten rid of all these multiplications completely by that product relaxation. Okay, so that's kind of one approximation. And there are a number of other approximations here. In particular, the two other approximations are sum and delay. So the sum approximation, if you look at that long equation here, okay, so that long equation, this is saying I equal to 1 to m minus 1, and this is one more thing. So if we approximate, we have already argued that this product here, if I assume that's almost 1, and then that's just adding these m quantities. So if I assume that product of A's are about 1, and then that's adding this m minus 1 plus that term, so that's just adding m things, and that could just be approximated by m times un. So that's what is called the sum relaxation. Okay, so that's the sum relaxation, and then if this input u is close to 0, then this m can be removed, and that can just be un. And the last approximation is really the delay relaxation, and the delay relaxation says I'm now computing yn using the past y plus this a times u, and if we apply this delay relaxation, then we can express yn as a function of yn minus m plus that whole thing here, the pre-computation again. So, okay, before I get to the delay relaxation, it is probably a good idea to see what we are approximating here. So the sum relaxation, so the product relaxation. So after the product relaxation, we got rid of all these multiplications. So start with the coefficient a, 1 minus that, multiply by m, 1 minus that, and that's fed here. Okay, so that's the result of getting rid of all these multiplications. Now with respect to the sum relaxation, all these things can simply be replaced by m times u, 4 times u. So that's the effect of sum relaxation. So the sum stays as it is, this is product relaxation, and here the product stays as it is, and that's the sum relaxation. And finally, the delayed gradient idea, what the delayed gradient says is that if I assume, so if you think about this term a n u n, in practice in the LMS adaptive filter, this would be the equivalent of the gradient with respect to the mean squared error. And so if we assume that gradient to be slowly varying, then we can replace that sum here by this n minus m prime minus I. So what it is basically saying is that I can replace this gradient, current gradient, by the delayed gradient, and the delayed gradient is delayed by m prime clock cycles, So there is a little difference between this m and m prime, and the m prime basically is the amount of the gradient that is delayed, and this m is the weight of that delay, where y is computed using y of m cycles before. So if we take all these three ideas that we have talked about and apply that to least mean square adaptive filter, so the filter equation here, En is equal to d minus d hat, the desired estimate, which is d minus the filtered output, the inputs filtered by that weight w, and that w is being adapted by the least mean squared algorithm. So wn is wn minus 1 plus the learning rate mu times the gradient is the error times the input u. Okay, so then if we apply these relaxation ideas, then we can write that as wn is equal to wn minus m2. So m2 is the number of delays in the weight update loop, plus all these quantities. So this is simply same as look ahead, just iterating that equation so many times, and then to that, then I can apply the delayed gradient idea. So just replace E times U at time n by E times U at time n minus m1. Okay, so if we do that, then that is the new weight update algorithm that has m2 delays as part of the feedback loop to update the weight, and the gradient E times U is delayed by m1 clock cycles. And then I can approximate that sum. Instead of m2 quantities being added, I can approximate that by some m2 prime. Okay, so that's really, these are some of the main ideas. And again, if you are doing a PhD and writing a PhD thesis, you come up with a few fundamental ideas and then apply that to various filters. And that's what Naresh was doing as part of his PhD thesis. And so the basic structure here, this so-called pipe LMS or pipelined LMS architecture. So if you start with the input U, that's the received signal, received from some kind of channel, and the filter block is computing an estimate of the desired signal D hat, and then we have the desired signal Dn, and then we do the plus minus and compute the error. And what you see here is this input delayed by m1 and the error delayed by m1, and that's what is the delayed gradient. We are delaying the gradient E times U by m1 clock cycles. And that weight update Wn is computed using Wn minus m2. That's the output m2 clock cycles back. Okay, so that's essentially the delayed LMS adaptive filter with all kinds of approximations. And those of you who wonder about, are these ideas useful? And so this delayed gradient idea is really what is used by Microsoft in the so-called pipe dream to speed up the training of deep neural networks. And that was part of Nanda's PhD thesis. And if you read the layer pipe paper, that's really that's the main idea that we are deploying, the delayed gradient idea. So the basic ideas are very useful, as useful today to train deep neural networks as they were used to pipeline least mean squared adaptive filters. So the basic essence, whether it is the stochastic gradient descent used in deep neural network or the LMS, they're all the same algorithm. There is, people say they're different, they aren't really that different. The training algorithms are same, these are same adaptive equations used in different contexts. Okay, so okay, that's what is a delayed LMS. So both the IIR filters and the delayed LMS, these are all linear equations. So the equations are simply linear computations. And so one of the problems, as soon as I came to this university long ago, and that's really 35 years ago. So one of the problems that I was thinking about, okay, so we have understood how to pipeline the IIR digital filters, which are linear equations. These are recursive digital filters, simple linear equations, and we can apply look ahead. And how do we apply look ahead to pipeline recursive loops, pipeline or parallelize recursive loops that have non-linear operations? And there are a number of DSP algorithms, particularly adaptive filters, that have non-linear operations inside the feedback loop. And so, for example, we list a few here: the adaptive differential pulse code modulation, ADPCM, which is used in speech coding, and the decision feedback equalizer, DFE, which is used in many signal processing applications, including transmission through all kinds of media, copper cables, fiber cables, wireless, all kinds of media. Okay, so how can those algorithms be processed with higher speed? So and it turns out that the idea is really very simple, as always, the idea is after the fact. If you have solved the problem after the fact, the ideas seem very trivial and very simple, right? And that's kind of many times, and so if we start with this feedback loop that I have shown here, which is take an input, and then there is a past state multiplied by some time varying coefficient alpha n. Again, the time varying coefficient is being adapted. There is another loop that is adapting that I'm not showing here, and then alpha times the input u plus alpha times the output x times the input u is now fed into a quantization device. So the quantizers are part of many DSP systems. You can think of in simple modulation schemes like pulse amplitude modulation or quadrature amplitude modulation. We are mapping these to known constellations, and so ultimately these are being quantized to, if it is simple BPSK, binary phase shift keying, which is 1 or -1, or if it is pulse amplitude modulation, PAM4 for example, 4-level pulse amplitude modulation, then they would be mapped to ±1 or ±3. Okay, so there are also schemes that use PAM5, pulse amplitude modulation of 5 levels, particularly used in gigabit Ethernet standards, and that's the standard that's bringing gigabit Ethernet to every PC or desktop or laptop device, as well as bringing data at gigabit rates in modern cars. Okay, the cars have many chips used for different kinds of transmission at different rates. So if you look at the simple critical path, the critical path is this multiply and add and the time to quantize that output. Okay, so how can we reduce that critical path? And it turns out that we could reduce that critical path by getting rid of the multiplication that's part of that feedback loop and now push that outside the feedback loop. Okay, so here is the main idea. The main idea is that we are trying to wait here to quantize. So I can perform that decision whether it is B1 or B2, which could be ±1, for example, until I go through the multiply and add. But the simple observation that this output of the xn is not taking infinite values, nor is it analog. So this xn is really either B1 or B2. So the number of values that xn takes is only 2 in that loop, which means then that I can pre-compute. So we are multiplying alpha n to either B1 or B2. So this output must have been one of either B1 or B2. And that means I can start with alpha n, multiply that to to B1 and B2. So multiply to both. I don't know which one, but multiply to both, and add that quantity to the input UN. So now we are able to compute alpha n times B1, if it was this was B1 plus input UN, and alpha n times B2 if that was B2 times UN. And I don't know whether it was B1 or B2, I have no idea, but that's okay. That's okay. So we can quantize those outside the feedback loop. So we now have a binary variable x1n. X1n is binary that takes 0 or 1 value. So think about this as a 2-to-1 multiplexer. And if that x1n is used now as a control signal, what you see here is that the two AND gates and the OR gate is simply a multiplexer. And so we have pre-computed the quantized values. And if you look at that mux here, let's say B1, okay, let's see what we decided here. B1 is x1n is 1, B2 is 0. So if x1n is 1, xn is B1. And if x1n is 1, I choose the path B1. So that output, this is chosen if it is 1, this is 0. So what we have been able to accomplish by pre-computing alpha n times B1 plus UN and quantizing that, and alpha n times B2 times B2 plus UN and quantizing that outside the feedback loop as a part of the pre-computation part, and then only the iteration bound or the loop bound is now only the time to compute a 2-to-1 multiplexer. And that's the idea of really what we call parallel branch and delayed decision, because we are basically saying that we can compute all the values of the branch. The branch here is taking two possible values, B1, B2. I mean, this again, some of these ideas have been used in compiler optimizations, and a lot of the work that I was doing in those days are taking the ideas from computer architecture and compiler optimization and applying them to DSP. And so that's really, that's the way that we can get rid of all these computations as part of that feedback loop and push them outside by that parallel branch delayed decision idea. Okay, so that idea is very, very useful. It was picked up by numerous companies, in particular people trying to build gigabit Ethernet using pulse amplitude modulation 5-level PAM5. And so clearly this paper came handy to them, people working at Bell Labs or Broadcom and later at Marvell and other companies. So the PAM5 idea is very similar. We have a 5-level modulation scheme that takes values plus minus in the PAM5. Let's see, I think the plus minus 1, the 5 values plus minus 3, and maybe one more, I'm not quite sure. We can surely take a look. Maybe, okay, it could be, yeah, we'll take a quick look. So anyway, and then the idea was that pre-compute all possible solutions corresponding to those modulation values. And that's how the parallel decision feedback decoder in the gigabit Ethernet receiver could be pipelined so that it could achieve the desired throughput. So maybe we'll take a quick look and see how that thing works, the gigabit Ethernet receiver. There are more things in the paper, a couple of ideas here. What happens if the number of quantization levels is 4 instead of 2? So that's again very, very Similar assumptions, if we have 4 levels, B1, B2, B3, B4, so take the quantity alpha n, multiply by B1, B2, B3, B4, all of these, add them to the input U, and then quantize these. You see here there are 2 quantizers, Q1 and Q2, and that's because when we have, so what I need here is a 4 to 2 multiplexer, right? So this is a 4 to 2 multiplexer because the output here is a 2-bit output. So the 2-bit output is input to this mux to decode the signal as B1, B2, B3, B4, and these 2 control bits are fed back to this 4 to 2 multiplexer, and so that's why we need to have these 4 inputs here and then 4 inputs at the bottom mux, and we are computing Q1, Q2, and that's because we need to adapt, we need to define 2 binary values, 2 binary Q functions, Q1A and Q2A. Q1A is 1. Okay, so if you look at both of these equations, you can map this to a truth table Q1, Q2, and the output of the quantizer. So if this is 1, 1, Q1 is 1, Q2 is 1, then this is B1. This is B1 or B2, B1 or B3. And that is really what you see from that feedback equation. So Xn is B1 times X1, X2. If X1, X2 these are the binary variables. If these are 1, 1, if the X1 and X2 is 1 and 0, then that is B2. Okay, so Q1 is 1, Q2 is 0, and the common part is B2. Okay, so we need these 2 binary variables, and those binary variables are used as control bits to the 4 to 2 multiplexer, and then so the feedback loop time is now this 4 to 2 multiplexer time as opposed to all that multiply, add, and the quantization device. And so that's kind of how we can accommodate multiple level quantization device. The next extension to that is a second order 2-level quantization. So let me just see if I can walk through. So these kinds of ideas are okay. There's a whole idea of second order. Okay, let's take a quick look here. So the second order 2-level. So what that means is, okay, if I go back to that previous diagram. Okay, so this, think about nothing but the second order IIR loop. So start with this Xn and then delay that by 1 more and delay that by and multiply that by some other quantity. So this alpha n and by something else beta n and add that. So that becomes the second order. So 2-level device, still 2-level device in the inner loop, but this is a second order feedback loop because we have the first multiplication with one delayed output and then the multiplication by beta n by another one. So what are the possible pre-computation levels here? How many things do I need to pre-compute? So in the first example with 1 multiply, it was just alpha times B1 plus UN. So now I need to compute 4 things because so again there are 2 states. These are 2 states. 2 states can be encoded using 2 binary variables, and the 4 possible quantities that we need to pre-compute. So alpha n, so this state here, this could be B1 or B2. This quantity here could be B1 or B2. So the total number of values that these 2 things can take together would be 4 possible values. So the number of things that we need to pre-compute could be alpha times B1 plus beta times B1 plus input U, alpha times B1 plus beta times, if this was B1, that was B2 plus U, and if this was B2 and this quantity was B1 plus U, and alpha times B2 plus beta times B2 plus U. So we need to pre-compute 4 things. Similar to these 4 things here, but in a different way. And if you think about this as a 6-tap DFE, a 6-tap decision feedback equalizer, so we have 6 delay elements, 1, 2, and then 3, and 4, 5, 6. Then the total number of things we need to pre-compute would be 64, 2 to the power 6. Why 2? Because there are 2 possible values, and 6 of these states could take either of the 2, so that would be 2 to the power 6 things to pre-compute. If this was a 4-level quantizer, I had 6-tap filter or DFE, then that would be 4 to the power 6, because any of these 6 quantities could take 4 possible values, so that would be 4 times, etc., 4 to the power 6. So that is so yeah, that's the main idea of how we can reduce these decision feedback equalizers to simply one multiplexer inside the feedback loop. And so again, as I mentioned, companies like Rambus jumped on that and used that to speed up interconnect, on-chip interconnect. So later on, people became interested in using these kinds of DFEs, decision feedback equalizers, in many other applications, in particular backplanes, serializer, deserializer. If you think about the copper interconnect in the on-chip, chip-to-chip interconnect and fiber communication. When you are transmitting data through the optical fiber, there is a lot of dispersion happening through the polarized mode dispersion, and a lot of the dispersion through the optical channels could be eliminated by electronic equalization, and those are based on these DFEs, decision feedback equalizers. And it turns out that the optical fibers are always running at tens of gigabits per second, all the way to 400 gigabits per second, and it is really very hard to operate even if, so this is the same example that from the previous 1991 paper, that if we had a 2-tap DFE with a 2-level device, decision device, I could pre-compute these 4 things, and then we just have the 4 to 2 multiplexer as part of the feedback loop. But it turns out that that is still not sufficient to meet the throughput requirements of these serializers, deserializers used in backplanes, or the electronic equalizers for optical communication. And so how do you pipeline? So okay, we have already reduced the DFE critical path to simply a multiplexer loop. And how do you pipeline or parallelize that simple multiplexer loop? And that by itself is non-trivial. So if we have a multiplexer loop and we want to pipeline or parallelize that multiplexer loop, that's not trivial. And it surely was a problem that several companies were facing. And well, you have to read the paper to see the companies. But so the paper talks about how to achieve 10 gigabit per second transmission through a 6-tap DFE. 6-tap DFE, 6-tap decision feedback equalizer. You have this D1, D2, D3, D4, D5, D6, and there are these 6 delay elements. You can think of them as states. So this 1, 2, 3, 4, 5, 6. Okay. And then there are these coefficients. Okay, so we can then say, okay, well, I mean, we can reduce that long critical path to this 64 to 1 multiplexer loop. Okay, so I won't go through all the details, but I think, again, this whole, in order to apply look ahead to these binary variables, and I can tell you now we are dealing with binary variables, so this is surely nonlinear because these are now binary state variables. If it is 64 to 1 multiplexer loop, you can think of that there are 6 binary variables that we are trying to update. So there are some of these equations. For example, an minus 1 is equal to an, okay, let me start from the first equation. An, this says here that an so this is an minus 1, the next state an is equal to, I pre-computed some cap an, so an, if this quantity is 1, you pick an, if that quantity is 0, a bar, then you pick bn. Okay, so that's the multiplexer loop, and in order to apply look ahead to that kind of loop, so first thing we do is replace n by n minus 1. Okay, so just replace n by n minus 1, then we get an minus 1 using an minus 2 and an minus 2 bar. Okay, so what we are interested in is substituting that an minus 1 here. So ultimately I'm trying to compute an using an minus 2 and an minus 2 bar. That's really what I'm trying to use. So we want to compute an using an minus 2 and an minus 2 bar, and these f quantities can be pre-computed, and if I do succeed in expressing that, then all I can say is, okay, I've replaced this an by some pre-computed quantity f, this by some pre-computed quantity another f, and then there are 2 delays in the loop. Okay, so having that 2 delays is important to us because those of you who took the other class, the unfolding algorithm can be applied to parallelize this so that in the parallel filter each of these will become 1 delay. I'm not going to talk more about that because it's hard to follow unless you take next semester's class, but it can be done. So we can parallelize, but before we parallelize we need more delays in that loop. So there is a little trick that goes into that recursion look ahead. The trick is that I can replace this an minus 1 by that quantity here in terms of an minus 2 and an minus 2 bar. But I also need another equation to replace an minus 1 bar in terms of an minus 2 and an minus 2 bar. Okay. Now where is that equation going to come from? And that's the non-trivial part. I mean, it's non-trivial until I tell you the answer. And once I tell you the answer, it's no longer non-trivial, it becomes trivial. Okay. So this is a binary state update equation. We are expressing a n minus 1 in terms of a n minus 2 and a n minus 2 bar, and all it is telling us is if a n minus 2 is 1, this quantity is a n minus 1. If a n minus 2 is 0, that quantity is b n minus 1. So there is no equation to describe a n minus 1 bar, but it's very easy for me to write down an equation. A n minus 1 bar is a n minus 1 bar times a n minus 2 plus b n minus 1 bar times a bar n minus 2. Why is that? Well, if a n minus 2 is 1, if this quantity is 1, then this quantity is cap a n minus 1, which means that the a bar quantity must be the complement of a n minus 1 or a bar n minus 1. And if that quantity is 0, this a is b, so therefore a bar must be b bar. And these a and these b's are also binary. So you just complement them, and that's the equation that didn't exist. And you have to think a little to take those equations, and then you substitute those equations, these two equations here for a n minus 1 and a n minus 1 bar to get that equation where we can pre-compute this fn1 and fn2. And if we do that, that's the loop that we get. So for example, an is now being updated using an minus 2. If an minus 2 is 1, then depending on this cap an minus 1, that's the control bit to that mux, it's either an or bn, and if that was 0, then we have another 2 to 1 mux. Depending on control bit bn minus 1, we select this or that. And so so that's the non-trivial part, how to generate these binary recursive equations and keep updating them, and surprisingly, or maybe not so surprisingly, after my spending quite a lot of time with all these equations and of course using many pages of papers to derive these equations. So if I was interested in using that same kind of idea that we showed here for a simple loop like that, that's with one delay as part of the feedback loop. Now if we have a if we have a 4 to 1 multiplexer loop here, so this is based on 2 binary states. If we have 2 binary states, so and then the inner loop, now we have used look ahead to increase that number of delays from 1 to 2, and that says that, well, we can have these extra 4 multiplexers, extra 4 2 to 1 multiplexers outside the feedback loop that we can pre-compute. And there is still more work to be done because because these 2 delays are sitting here doing nothing. I mean, you don't want these 2 delays that are sitting in a lumped manner. And the way to really take advantage of these 2 delays for achieving higher speed is to parallelize this by factor 2 using unfolding algorithms. So that's where unfolding comes into play, and these feedback loops have to be pipelined using look ahead and then unfolded and retimed to really achieve the true critical path. And so that kind of an idea is applied here to many places. So this is 8 to 1 multiplexer loop, and you can see here the 3 levels of nesting. So there are 3 levels of nested feedback loops. the inner loop has 2 delays and the outer middle and outer loop has 1 and 1. So, and there is one extra stage of pre-computation using 8 multiplexers, and that 8 is 2 to power 3. And if you take that same 8 to 1 multiplexer loop and replace the inner delays from 1 to 3, 1 to 3, we get this 8 extra delays, 8 extra multiplexers in this stage and in that stage. And the fortunate thing is that if I wasn't clever, if I wasn't smart, I would need 64 8 squared multiplexers, but because of the way I reduce the pre-computation complexity, so these are now 8 plus 8 as opposed to 8 squared. So the pre-computation overhead increases linearly with respect to the speed up as opposed to exponentially. So that's kind of those are some ideas for how the decision feedback equalizer can be pipelined and processed in parallel, because ultimately these have to be unfolded and processed in parallel to achieve the true speed up, because the true speed up is not here. These 3 delays are sitting lumped, doing nothing. Nothing is happening. But in order to get the true speed up, you have to unfold this by factor 3 and get a parallel structure that processes 3 input samples in 1 clock cycle. Okay, so that is kind of one application. So I can quickly go through one other application. Let's see here if we can quickly take a look at the 10 gigabit Ethernet. So when the IEEE was standardizing the 10 gigabit Ethernet, again that was considered impossible because of another kind of nonlinear operation in the feedback loop. So let me see if I can, so that let's take a look at this paper here. Okay, so the so-called Tomlinson-Harashima precoders, and this is part of the 10 gigabit Ethernet standard IEEE 802.3an, and so what's the main difference between what we have been studying, the linear IIR filter versus, well, we looked at DAP or the ADPCM has a decision device. So the main thing about the Tomlinson-Harashima precoder is it has another kind of non-linearity as part of the feedback loop. It is not a simple IIR filter because of the non-linearity, and the non-linearity in the DFE was the decision device, and the non-linearity in the so-called Tomlinson-Harashima precoder, which is part of many communication systems, and in this particular paper it's talking about how to parallelize the Tomlinson-Harashima precoder for the 10 gigabit Ethernet that brings data to the computers that can operate at 10 gigabit rates. Okay, so the non-linearity here is modulo device, modulo 2m. Okay, so again there is a parameter m. Okay, so how can we achieve parallelism and increase the clock speed or the sample speed of these devices? So again, you can see the critical path as we have talked about. The critical path is 1 multiply add, another add, and the modulo. So that's the equation 4, that's saying that the critical path here is the 2 times add plus multiply plus the modulo device. Okay, so By the way, how do we, okay, so I mean, I talked about this decision directed equalization. How do we get the, let's go back to that 1991 paper. Okay, I still don't show it, but anyway, so how do we get the, so when these are being adapted, there is a desired signal. Okay, so how do we get the desired signal in a typical communication system? How do we have a desired signal? Okay, so so in a typical LMS adaptive filter, if we are transmitting some symbols in a communication system, for example, in a transmission system, okay, I mean, if I am transmitting signals, what might be that desired signal be? The desired signal is something. Okay, this is the receiver, right? So the receiver, this is the receiver. Receiver is receiving the received signal called UMN, but it doesn't know what the transmitter desired to be the desired signal. So how does the receiver know what the transmitter had desired? Any thoughts about that? Anybody has heard of pilot tones being used in communication systems? Yeah? Pilots, yes. So that's the desired signal. The D of N is the pilot tone. Anytime you are transmitting symbols, you are transmitting pilot tones that are known to the transmitter and the receiver knows the pilot signal, that's the desired signal, and it uses that to adapt all these coefficients. Okay. So that's the pilot tone, that's part of the information payload, that's part of the payload. Okay, all right. So let's go back to that. Yeah. So what's the difference between so-called equalization and the receiver? I mean, what we are doing with the adaptive filter here is the equalization is being carried out in the receiver. What is the difference between carrying out the equalization in the receiver versus transmitter? What does it mean to equalize in the transmitter? And whenever we equalize the signal in the transmitter, that's called the transmit equalization, which is really the precoding. That's the precoder. Okay. So what does that really mean? Okay, you think about what are we trying to accomplish. There is a channel, whether it is a wireless channel or a copper cable or a coaxial cable, it doesn't matter, or a fiber cable, all of the channels are distorting signals, they are attenuating signals, they are providing a frequency response to the signal. And so if you assume the channel H, okay, let's look at the figure A on top left. If you assume the unit sample response of the channel H, and all we are trying to do at the receiver is mimic an equalizer that achieves the transfer function 1 over H so that it cancels out the effect of H, and that's all we are trying to do. So the channel filter H combined with the equalizer 1 over H in the receiver is trying to overcome all the attenuations and frequency dispersions and all of that. Okay. So whenever we try to equalize in the receiver, we are trying to adapt those coefficients that I showed here. These coefficients ultimately will reach 1 over H. Now the argument of transmit equalization is, instead of equalizing in the receiver, I can take the information that I am trying to transmit x of n and mimic 1 over h in the transmitter as opposed to cancelling that or equalizing that in the receiver, and that's what is called precoder. Precoder means we pre-code or pre-equalize, and if you look at this transfer function 1 over 1 minus the loop gain is 1 minus h, 1 minus the loop gain is h, and then 1 over h, and the effective transfer function of that so-called pre-equalizer is 1 over h, and 1 over h is simply trying to overcome the effect of h, and h multiplied by 1 over h is simply 1, or in the time domain is delta n, which is means that we are able to get the transmit signal xn at the receiver. Okay, so all right, so that's the basic idea of transmit equalization, or the so-called Tomlinson and Harashima precoding. Okay, discovered by two different people, Tomlinson in Japan and Harashima in Japan and Tomlinson in the US, and named after both of those people. Okay, so so the pre-equalizer has this modulo device mod of 2m, so it takes m possible values, so this T of n transmit value takes m possible values, and this is modulo 2m, and so how do we achieve parallelism in this precoder? And to achieve parallelism in this precoder, the first step, the very first step, again it was a non-trivial problem. Non-trivial because we have a non-linear device as part of that feedback loop, and the first step to understanding how to parallelize or pipeline, how to parallelize that, is to get rid of that modulo device and replace that by adding a compensation signal B of n. So think about B of n is some constant times 2 times m. So what is going on here is we are dividing by 2m and computing the residual, and residual is being transmitted, that's the transmit signal Tn. So I can say, okay, so this Vn, if I could add Vn, which is whatever the quotient was, when I divide by 2m, there's a quotient, there is a remainder, and the remainder is T of n, whatever the quotient was. So this Vn is that quotient times 2m, and that's a compensation signal that I can add to that, and then I can treat this whole thing as a simple IIR filter and apply the look ahead to this equation here, and then finally substitute back that compensation signal that can be derived from the T of n. So that's the equivalent idea. There is a little bit of manipulation that goes into that. Okay, so once we are able to remove the modulo, first we are able to remove the modulo. Okay, so this is after whatever you have done in the class, this is exactly same thing. This is a parallel IIR filter. Everything is same. There is one delay. So we are computing T of 2k plus 1 and T of 2k plus 2 using the past values T of 2k minus 1 and T2k, and these compensation signals are still here, V2k plus 1 and V2k plus 2. That's not helpful, that's an intermediate step. Ultimately, I don't know what the Vk is, and we have to get those quantities back, and then if you look at how so after we have that equivalent circuit, then we put back these modulo devices into the feedback loop, and the modulo device now creates V2k plus 1. So it goes through that modulo, and then it gets the quotient, and the quotient is V2k plus 1. Okay, so that is how we can parallelize, and it again takes the two information symbols x2k, x2k plus 1. I can always tell you all the companies that are selling 10 gigabit Ethernet chips are using this idea. So this was Yongru's PhD thesis. Yongru worked for a number of years at Newport Media and now has his own company. He founded his own startup, I believe, In Play Tech, something like that. So he is developing new chips. Okay, so that's kind of the idea of parallelizing the Tomlinson-Harashima precoder. That's part of 10 gigabit Ethernet chips. Let me see if I can quickly go through the gigabit Ethernet chip and how that makes use of the DSP that I talked about. So I believe this was 2002. Companies were working on that sometime around 98, 99. So all the first chips were sold in 99, I believe. So those chips that used to implement gigabit Ethernet transceivers were realized using this coax copper cables, so-called category 6 twisted pair cables. Okay, so so let's take a look at this 2001 paper. From Journal of Solid State Circuits. So this is how the gigabit Ethernet standard works, IEEE 802.3ab. Okay, so what is going on here? So if you look at the coax cable, that has 4 different transmitters and receivers. So this is the transmitter and the right side is the receiver. So at the transmitter we have transmit as well as receive, and there are 4 such independent transceivers. So each of these transceivers is operating at 250 megabit per second. So there are 4 transceivers in the twisted. So think about it as 4 twisted pair cables. Okay, so in that twisted pair there are 4 transceivers, each operating at 250 megabit per second. Each of these transmitter receiver is receiving information at 125 megabaud. 125 megabaud. The baud rate or the symbol rate is 125 megabaud, and these are effectively achieving 2 bits per information, 2 bits per information. So think about equivalent of PAM4, but it's really PAM5 because there is some trellis coding built into the modulation scheme, trellis coded modulation. So that provides some error control coding, and that makes it PAM5 as opposed to PAM4. Okay, so effectively 2 bits per symbol times 125 megabaud, that's 250 megabits per second, times 4 transceivers, that's 1000 megabit per second, or 1 gigabit per second. Okay, that's how. But what are the real challenges? The real challenges are inside each transmit receive. There is its own echo. The receiver has to cancel the echo of the transmitter and has to cancel the near end crosstalk next from the 3 adjacent transceivers, and has to cancel the far end crosstalk coming from the far end. So these are the challenges. So there will be 4 echo cancelers, 1 per transceiver, 12 near end crosstalk cancelers, 3 near end crosstalk cancelers per transceiver times 4, 3 times 4, 12, and 1 far end echo. So okay, far end echo is negligible, so you can ignore that, and then 3 times far end crosstalk from the transmit receive in the far end. So think about it, in old days when you were calling your friend in San Francisco, you get your own echo back. That's the own echo canceller. And then there is a far end echo coming back. That is a lot less than the effect of this echo or next. And these are cancelled out by filters. And there is a sophisticated trellis coded modulation that goes into these construction of this modulation scheme here. But the 5-level PAM5 that I talked about are values are 0, plus minus 1, plus minus 2. Those are the 5 levels. And those 5 levels are, so all the decisions with respect to those 5 levels can be pre-computed. So that's the long feedback loop, and that long feedback loop, and similar to the quantization loop that I showed. And so for the 5-level decisions, they can be pre-computed and pushed outside the feedback loop, and that really enabled these gigabit Ethernets, because 125 megabaud means they had to have 8 nanosecond clock that can perform all of these. And let me tell you, most of the smartest engineers couldn't do that, and a lot of companies were pushed out of business after spending a lot of time, because they couldn't. You had to use that idea of DFE pipelining just to push out all those. You can see all those operations being computed here are computed outside the feedback loop, and that's how they were able to achieve the 125 megabaud rate. So that's the 1991 paper that they are using to speed up the receive or design of the gigabit Ethernet. Okay, so these are some of the. It is true that the simple IIR filter pipelining itself may not have much practical impact, but the idea that came out of that have had tremendous impact. And whether in simple Ethernet or 10 gigabit Ethernet, or in other backplanes and serializers, deserializers. By the way, how important Ethernet has been for everybody's life, the ACM, SCM Turing Award this year went to the inventor of the Ethernet. Okay. So I will stop with that. We can continue our office hours after the class. I think I forgot to bring your graded homework that the TS would have left on his desk. I didn't stop by, but I'll bring that on Wednesday. So of course, what I'm teaching today won't be in the exam, so that's just for understanding a few ideas. I am happy to teach more concepts next class or review exam depending on what you want me to do. If you want me to review some specific concepts, just email me, or if you want me to go over some problems, email me. Okay, with that, we will stop.